All right, now let's do repeated eigenvalues with matrix exponentials. And I'm sure your first reaction is, Mama, no! But don't worry, this will be so much easier than matrix exponentials, and in fact, easier than generalized eigenvectors. We won't need any of that. So let's solve x prime equals ax using matrix exponentials, where a is the matrix -1, 4, -4, 7. And it turns out all you need are the eigenvalues. You won't even need eigenvectors for this. So let's find the eigenvalues. And let me actually do this because it's been a while. So let's do determinant of a minus lambda I. So -1 minus lambda, 4 minus 4, 7 minus lambda. So AD minus BC. So -1 minus lambda, 7 minus lambda, -4 times -4. And so -7 plus lambda, -7 lambda, plus lambda squared, plus 16. And then we then get lambda squared minus 6 lambda plus 9, which is a perfect square. Just like you're perfect squared. And you set this equal to 0, and you then get the repeated eigenvalue lambda equals 3. Repeat. And once again, the good news is you won't need any generalized eigenvectors. You won't even need any eigenvectors. We can actually find our solution using just the eigenvalues, which is kind of crazy if you think about this. But I do want to mention, so some people try to solve it using A equals PDP inverse. This actually doesn't work in this case because there are not enough eigenvectors to form your matrix P. So you can't actually go that route, and we need to go a slightly different. So step 2. And for this, I would just like to remind you, so we're going to use the power series definition of the matrix exponential, which is 1 plus AT plus AT squared over 2 factorial plus dot, dot, dot. And the point is, usually this is an infinite series, but it turns out in this specific case, this infinite series just becomes a finite sum. A sum of 2 terms, actually, because it turns out, in this case, if you take A and subtract the eigenvalue, so A minus 3i, and you square this, you just get the 0 matrix. 0, 0, 0, 0, which you will see is the key of turning this infinite series into a finite sum. But before you get too overexcited, I do want to mention this trick only works for 2 by 2 matrices with one eigenvalue. For 2 by 2 matrices with one eigenvalue. Which we do have here, actually. So that's a nice thing. Okay, so how do we do this? Well, let's start with this e to the at, because that's what we want to calculate. And well, we do want the a minus 3i to appear here. So a minus 3i. But again, we have this t, and that's the t. And well, to remedy that, we need to multiply it by e to the 3it. Now, it turns out you can use a definition of e to the 3it, and it turns out this is the same as just multiplying by e to the 3t. So we have e to the 3t times a minus 3it. And now the whole point is we can use power series. So this is the same thing as e to the 3t, and then 1 plus a minus 3it plus a minus 3i squared t squared over 2 factorial plus other terms. But wait a moment. We have a minus 3i squared. Didn't I just say it's 0? Yes, it is. So it turns out this whole t squared term actually becomes 0. And same for the cube terms and the fourth terms. So after this whole dust has settled, we end up getting just e to the 3t and an I plus a minus 3it. A much simpler sum. And we can calculate this. So this is e to the 3t and then 1001. And then we had, I think, minus 1 minus 3. And then 4. And then minus 4. And then 7 minus 3. And then times t. Which, if you want, you can simplify. This becomes e to the 3t 1001, and then plus minus 4 minus 4t. And in the end, we get e to the 3t and times 1 minus 4t, and then 0 plus 4t, so just 4t minus 4t, and then 1 plus 4t. And this, I want to remind you, we get e to the, that's e to the 8. Let me put it here. E to the 8. And remember, why is that useful? So this allows us to directly find our solution. So let's do that. So remember, x to the t was e to the at times constant 1, constant 2. And in the end, this just becomes c1 e to the 3t times 1 minus 4t minus 4t, and plus c2 e to the 3t 4t, and then 1 plus 4t. And that's all she wrote. You see, no need to find eigenvectors and no need to find generalized eigenvectors. Using this beautiful fact, we're able to turn this infinite sum into just a finite one and calculate the solutions.